So in this hands-on session, I'll try to, my ambition is to try to make you try all the different models that we have in Oceananigans and ClimaOcean. Probably it's not going to happen because there's a lot of computation that we have to do. So maybe we're going to skip the middle one and do one non-hydrostatic model simulation and then directly go to the global ocean, which is kind of ambitious because I want to do the whole ocean forced by an atmosphere, but let's see if we can do it. So all the notebooks should be in the GitHub page. Where are they? If you go to Julia, IO25, notebooks, day 4, hands-on session. No, this is the Alex one. Simone. So here I have all the notebooks. There's also project.toml if you wanna start from there. Otherwise, you can just add the packages, but yourselves. And I was thinking to show start with a 2-dimensional turbulence simulation, but I think that's kind of dry, so I kind of changed the simulation to a cabling simulation. Basically, cabling is what happens when you have fresh water that is at 2 different temperatures and at the same density. So fresh water has this weird equational state that has a maximum at 4 degrees Celsius. So if you take hot water on top of cold water that have the same exact density, you start mixing them, and you generate water that is denser and wants to fall. So what we're going to simulate is this kind of simulation here, where you have a hot water on top of cold water, hot water on top of cold water, and this is an unstable equilibrium. So in theory, this is in equilibrium until the 2 water masses mix, and when they mix, they generate a denser flow that starts to fall. Okay? So this is what we're going to try to simulate, first of all, just to get an idea of how the non-hydrostatic model works. Oceananigans and ClimaOcean are very pre-compilation hungry, so it will take a lot to pre-compile it. So if you can generate a kernel that has this O0 argument here, so we don't use any optimization, and the whole process will be a little bit faster. So if you don't know how to do, just open Julia, type using iJulia, and install a kernel that you can call it however you want, that has check bounds equal no, so we ensure that everything moves a little bit faster. You don't use any optimization, and if you have multiple threads, please use them so that we can get a solution quicker. All good? All good? Okay. Yeah.
Does Oceananigans and ClimaOcean automatically detect the number of threads?
Sorry?
Does it automatically detect the number of threads? So say here you...
Yeah, you should see something like this. When you start it...
So you should be able to just use -T auto.
Yeah, dash auto, and then you get like 8 threads or something. So when you start, you should see something like this. So it will inform you how many threads you're using. Okay? Good. Let me know when you have downloaded and opened the notebook so I can go through it. Locally, you can just do Jupyter notebook on the folder where you have the notebooks. This will open a Jupyter notebook instance. You'll find your notebook here. I kind of prefer to go to Jupyter Lab, but I mean it's up to you. And then you're gonna have your simulation ready. And if you install the different kernel, please select it over here. So you just have to go on the top right, where you have your kernel that you're using, And you're probably going to find immediately the new kernel that you defined. All good? Sorry? If you have Julia 1, with Julia 1.11, Oceananigans has some problems. So there's some numerical problems, weirdly, that we're trying to solve. If you have Julia 1.10, use it. If you have Julia 1.11, try it out and see what comes out. But I don't guarantee.
So the Cabalin notebook, right?
Cablin.ip, like the notebook.
You just use the Julia file, right?
Yeah, if you prefer using the Julia file, like I prefer using the .jl, so you can just start, Julia. And then you can just run or you can run it via VS Code if you prefer. I mean, that's, sorry? Check bounds equal no is, it elides the bounds checking in the arrays. So it makes everything faster. If you don't unnote with @in bounds everything.
Have you checked that actually has a real performance difference on version 1.11 after the effect handling changes?
Not really, no. We haven't really, because with Julia 1.11 we switch the CI crashes, so I really don't touch it too much until we figure out what's going on there. Okay. Is everybody good?
I can read which file is that because there is a lot of it small.
Here we go. Sorry. So we're loading Oceananigans and seawater polynomials. That is the package that we use to compute the density of seawater given a temperature. So it has all our equations of state. Okay, I guess I can go on. Pre-compiling, eh? Yeah, probably will take a while. Yeah.
Can I just see the terminal code you made?
You want to run through a terminal?
Yeah.
Okay. It might be. It might be. It might be. Yeah.
When you change the optimization
Yeah.
level and
Yeah.
when you change
Check bounds, yeah.
you'll need to recompile all your libraries because you should have different node beyond.
Yeah. Yeah. So if you are already precompiled, just go. Mm. Hmm? Sorry? No, it's a separate package. It's not in the project? Okay, sorry, then you have to add it. Let's see what I had in the project. Oh, yeah, you're right.
Works on my computer.
It's a very simple package, seawater polynomials. It just computes, given it just has all these algebraic functions that compute a density given a temperature and salinity. It's pretty lightweight. Okay. So, if you all started with loading everything and hopefully everything precompiled, we can start defining a grid. So in this case, the simulation that I'm showing here is DNS. So it means that we are resolving down to the Kolmogorov scales, which means the smallest scale, turbulence scales in the system. And this requires a lot of grid cells. This simulation was done with 2,000 by 2,000, with a 2,000 by 2,000 grid. I'm not going to make you do that. That's a little bit too expensive. So we're going to go in the LES regime. And LES means large eddy simulation, which means that we're solving only the largest eddy in the system and providing a diffusion or an implicit diffusion that is supposed to mimic the effect of subgrid scale turbulence on the large scales. So in this case, a grid of 256 by 256 is enough. It's quite a lot still, but it should be enough to run on your laptop. So we define a rectilinear grid that runs on a GPU. If you are on a CPU, if you are a GPU, please use it. If you have a CUDA-enabled GPU on your laptop, we are in the process to put in metal, but it's not there yet. Once there's going to be metal, we can do GPU metal, backend equal metal, and it will work on M1 GPUs, but it's not the case yet. And we define a domain that goes from 0 to 0.5 in X, 0.5 in Z, and we want it to be bounded in the X direction, flat in the Y direction. And by flat, we mean that we just remove that dimensionality. So we're going to have a two-dimensional grid, unbounded in the Z direction. So it's just basically a closed window, a closed box that is positioned in the XZ plane with 256 by 256 grid cells. And here you have a nice show method that summarizes the properties of the grid. So it's a regular space grid in both directions. I could put here an array, and this would give me a variably spaced grid. Length equal to 257. This will give me a variably spaced grid, but in this case, we just need a uniform grid, so we just give it a tuple, and this will build our grid. Now, we have to define the properties of seawater. So we use the TOS10 equation of state, which stands for equation of state of seawater 10 or something. Anyways, it's a very complicated equation that is a complicated polynomial with 50 terms that relates temperature and salinity to the density of seawater. And it depends on the gravitational acceleration. So we specify the gravitational acceleration of the Earth, 9.81 meters squared per second. And we want fresh water, so salinity has to be 0. So we just specify constant salinity with 0 PSU. All good? Ah, okay. You guys are fast. Now we specified the grid, we specified the physics. It's time to build a model. In this case, this is a non-hydrostatic model because the turbulence is non-hydrostatic. And by non-hydrostatic, we mean that we have a vertical acceleration term because the equation that Alexander showed were hydrostatic in the sense that in the equation for vertical momentum, you remove the vertical acceleration and you just keep the balance between pressure and buoyancy. In this case, we're solving for the acceleration for the vertical acceleration and the advection in the vertical direction. We use a Wino scheme. I think you have order 7. Put order 5 maybe because it's a little bit more faster for the moment. So, and we need to pass the buoyancy. So the buoyancy is the seawater buoyancy that we specified above here. And we need to evolve a tracer that represents temperature. That's going to be used to calculate the density and compute the buoyancy in the gravity term. All clear? All good? Okay. Well, so if you have to build a model, you can look at what we have built. So this is just a non-hydrostatic model on the grid that we have defined. In this case, we're using a RK3 time stepper. We know advection scheme. We have one tracer, no closures, because the diffusion that is required to express subscale motion, it's already implicit in the Wino scheme. We could also include an LES, a more let's say standard LES model by including a closure. For example, by doing something like this. Oops. These are all different closures that we have implemented in Oceananigans that express the influence of subgrid scale on resolved scale motion, but we don't need it at the moment. So let's just keep our Wien order 5. And I thought to make the simulation a little bit nicer, to set up the initial condition with the JuliaEO logo. So download the JuliaEO logo, and we set the temperature of the initial condition following the bounds of the JuliaEO logo. So just to show you what it looks like. Oh, display fig. Here we go. So this is our initial temperature. Yellow parts are hot, blue parts are cold. But all this at the moment has the same density because we have selected temperatures that give you the exact same density. And? Different temperature, but same density.
So the salinity is changed?
Salinity is 0. So fresh water follows this. This is the curve. Sorry, I should explain it better probably. This is the density of fresh water based on temperature. So if you take 1 degree Celsius and about 0 degrees Celsius and about 7 point something, 755 to be precise, you have the exact same density, but different temperatures. So in theory, this system here is in equilibrium, very unstable equilibrium. A minimum perturbation will make it all collapse because you'll form dense water around the borders, right? But in theory, this should, if there's no diffusion whatsoever, no motion, this stays like this, right? Is it clear? Okay. So now we have initialized our model. By the way, sorry, I didn't go through the initialization process. To initialize a model, you can write set model, and then the quantity model with either a function or an array. In this case, I have downloaded the image, transformed it into an array with the same dimension of the grid that we're using, and just passing it here to the temperature. No, actually, set up correctly the temperature to be hot where you have inside the borders of the image and cold outside, and then pass it to the model. And we also initialize the velocities with random velocity fluctuations because we don't want this to stay in equilibrium. We want this to start mixing. So we initialize with very, very, very small velocity fluctuation, like in the order of 1 e to the -4, to give like a kick to our model. Any question?
I have a slightly weird question. I can't run Jupyter notebooks on my laptop. I'm trying from the script.
Yeah.
That works the same thing.
Should do it. Let me try.
It's running now, so it's all right. But
Should be running, yeah. I just took the Julia script and literated it with literate.
Okay.
Because I don't use notebooks usually, so.
Thank you.
It works? You have already a video?
I don't have a figure, but it ran, so I will check.
Okay, you should have a cabling_2d.mp4 that shows you the video of your solution.
No, because I don't like that, so I will.
Okay. Go ahead. Change it how you prefer. So now we set the simulation. the delta t has to be small enough such that we don't incur in CFL problems. So when you run a fluid dynamic simulation, your delta t, you have to satisfy what is called a CFL condition. So basically, the ratio between your delta t and your grid spacing multiplied by your velocity should be smaller than 1. Otherwise, your information will jump more cells, and you eventually will, your simulation will crash. So a delta t of 0.1 is enough here. And we'll run this simulation for 100 non-dimensional time units. So in general, a model contains all the physics and the numerics, while the simulation contains all the details to run the simulation. So the delta t, how much is the stop time, how much is the stop iteration if you want to put a stop iteration, and all the callbacks that you want to do while time stepping. In this case, the callbacks that we have are just checking if you exceed the stop time, checking if you exceed the stop iteration, or checking if you exceed a wall time limit. And by default, we also add an and checker, so just to see if the simulation crashed or not. But here we'll add another callback, because we also want to make sure that we see what's going on during the simulation. In this case, it's easy to add a progress function. Callbacks accept the simulation as an argument and are called at a schedule. So in this case, what I'm doing, I'm just defining a function, progress, that takes simulation as an argument, extracts the velocity the velocities from the model, u, v, and w. In this case, v does not really do anything because it's a 2D simulation, so we don't really have to look at it. And I'm just outputting a string that contains that shows the iteration number, the time of the simulation, and the maximum of the w velocity, and the maximum of the w velocity, and that's it. And then I'm adding this callback function, this function as a callback to the simulation at a schedule of 10 iteration, at an interval of 10 iterations. This means that every 10 iteration, I will execute this function. Yep.
Your y-axis is the vertical?
Y-axis is flat in this direction. So.
It would be the vertical.
Yes. So x is the horizontal and z. Generally, in ocean modeling, the z-axis is always the vertical axis is always z. Generally speaking. Yeah. Okay. So we also have to collect some outputs. In this case, we're interested in temperature and density. So here we're extracting the density from the model. The density has to be computed. It's not really there's no field in the model that expresses density because it's computed point-wise and just used where it has to be used. We're just evolving temperature. So this function seawater density is extracting the density from the model. And we also extract temperature. And we pass it in a output writer. In Oceananigans, we have two different output writers, one that writes to netcdf and one that writes to JLD2. In this case, I'm using a JLD2 output writer. You have to specify the model as an argument and what type of fields you wanna save. In this case, just density and temperature. What is the file name where you save the data, and the schedule. So every when you're gonna save the data. In this case, I'm saving it every second. So I have a 100-second simulation and I save every second. Here, this argument is just to know if there already exists a file with the same name, whether to delete it or not, and to overwrite it. And then we can add the output writer to the simulation in the output writer's dictionary. Okay. So now if you look at the simulation object, we have added an output writer here that writes to this file on this time interval. Okay. Did I add the progress function? Okay. Everything good? Everybody's following? Everybody has a problem? Somebody has a problem? Yeah?
I know that the output writer goes, I'm trying to change it to NCD as well because I
It's better if you use GLD2. Because no, I tell you why. Because we have a utility that is called fill time series. That did I lose something here? We have a utility that is so this utility here grabs a variable from a GLD2 file, and unfortunately we have it only for GLD2. We haven't already implemented this utility for NetCDF. So if you want to visualize, it's better to do this. Like, this is much easier.
I mean, the thing is that visualization depends on person. So
Sure.
so that's why I would do things in my own I just prefer to have.
Okay.
I have a question for that. So simulation output writers, the code, yeah. So you have the colon GLD2, right?
Yeah.
What does that actually do?
This is just a dictionary. I can call it. So this output writer is a dictionary, and I am adding this output writer to this dictionary under this key.
Okay.
Doesn't have to, can be whatever you want.
Okay, so it can be anything, but it doesn't affect the type of outputs.
No, I mean, just don't have. If you want to write another output writer, don't call it the same way, because otherwise you're going to overwrite it.
That's fair.
Can I ask why you don't like GLD2 without a specific explanation?
I just don't.
In the meantime, I'll start running.
Size parameter changes. It's actually terribly small. If you add a field to any of these structs, after
Okay. By the way, I'll start running because it takes a while to run the whole thing. So, have you guys tried to run?
It took like 1 minute.
Okay, did it run?
Yeah, it did.
Okay.
But I'm reminding it running.
Okay. Okay, so this. Yeah. You have a GPU, nice. Yeah. I guess the plotting that we're doing will create problems. So you cannot plot directly from GPU. You have to convert the whatever it's on the GPU to CPU before plotting.
Yeah, you can kind of plot on the GPU, but it's
You can't actually like heat map something, some GPU query. Huh.
basically what you do is you map the CUDA buffer to OpenGL,
Ah. Okay.
and then it's just using the same.
Because probably you're setting with what if you do this? It should work without this, but
And one more thing about the GLD2, like if you want your simulations, if you want the data to be people that are often not using CUDA, GLD2 is not a solution.
oops.
You rather have standard CDF that I
I agree with that, and to be clear, I'm not the proponent necessarily of GLD2, which is very good to hear. That I have the same. When every time I mention this kind of file to somebody from the activity, and the lack of, I guess, mixing and breaks the first lessons of June.
Yeah, it's a pain when you change version of your package. They have to reconstruct the type. It's kind of annoying, but yeah. Okay. Have you guys run the simulation?
Mine is
Still
still running.
running.
But, I'm not using Jupyter
Mhm.
like this.
Okay.
I have downloaded the notebook.
Okay.
There are some difference between what you have on the notebook and what
What difference are there? Should I come to you?
Let's have an output, right, of collected density and temperature view 37 and there are some difference between the and the okay. But I don't know if the topology different let's see.
Okay, let's see. You'll let me know if it's different or not. Anyways, so now we have done the simulation. Everything has been saved down to JLD2 file, and we can visualize it. And for this, as I was saying to Nat, that we have this field time series option to load all the data in memory. If we don't want to load it in memory, we can also give a backend for large data sets to make sure that we load it lazily, because this is sometimes your JL2 file can become gigantic, but and these fields can be indexed into, so they'll have a dot times that will show what are the times that you have saved. But let me do it like this maybe, so I can show it better. Yes. So this is a field time series that we picked up from the JLD2 file. Is in memory, which means that everything has been shipped into memory, all the 101 time steps. We can inspect the times of it. So the times are every second starting from second 0 to second 100. We can index into it, and if you index into it, you get a field corresponding to the time that you uploaded. But the underlying data is 4-dimensional, it's not 2-dimensional. It's just, if you index into it, you just cut out the instance in time that you wanna index into. Oops. Boom. So last thing to do is plot. And here we use Karamaki for it. Let's plot. I don't know why Karamaki is this slow plotting, but it's a bit slow. Do you know? Mm-hmm.
For the density, the first time step, you're supposed to not see it vary. Are you supposed to see it vary with height?
Very?
Are you supposed to see change with height, the density?
I'll show you the video now. I'm printing it. So what I'm plotting is temperature on the left-hand side and density on the right-hand side. So I'm cutting, basically making a cut in half of the domain. On the right, on the left-hand side, you see temperature. On the right, you see density. And temperature is different because you start with a hot and a cold fluid following the JuliaEO logo, but density is all the same because of this weird nonlinear density.
Is lower at the top and higher at the bottom. That's what I'm asking.
Are you sure that's not temperature?
That's not temperature, because I looked at it separately.
Did you change the salinity?
No, I did not. I see what's changing.
Oops. So weirdly enough, plotting is taking more than the simulation.
Yeah, that's weird because I tried it and it took like 4 seconds.
Yeah, right. It should be like, I'm also using. Is it because it's threaded maybe? Does Karamaki work weirdly with threads?
No. Are you trying to thread the record?
Huh?
Are you trying to like thread the record?
No, but I launched this with threaded Julia.
No, it should be fine.
Should be fine, right?
I launched mine with threaded Julia.
Huh?
If you're visualizing, is it plotting the actual raster or something, or is it actually doing?
No, that's 256 by
256 by 256 subarray, so nothing really special. I don't know. I see it's probably my laptop. I don't know. Probably it's my laptop. If for you went fast, it's fine. Then it's just my laptop.
No,
Yeah.
we have like practically the same laptop.
Yeah.
Okay.
I don't. This is M1.
Yeah, same.
Same. Okay.
That's weird.
Okay. Well, if you guys have the simulation, does it run?
Did you display this on something else? Or you didn't display it at all?
Ooh, maybe I displayed it. No, it doesn't look like, no. Huh. Probably is this that is taking time. This is basically indexing in the.
No, that's in memory.
Yeah, it's indexing into memory. Wow, I don't know. Also for me, like it's weird because usually it doesn't take that much.
Yeah,
But anyways, so if everything has went well, you should have a file in your folder called cabling2d.mp4 that looks something like this. So density starts constant, temperature is different, and once you start time stepping, the boundaries start diffusing, and you get a denser fluid that starts falling to the bottom. Now, bonus question: what will happen if I put salinity equal 4? If I put some salt in the system? Nobody wants to guess? So what will happen on my blob of to all of it. I'm adding a constant salinity of 4 PSU to the system. So now it's not fresh water, now it's salty water.
I think it's stable, no? Especially because it's now warm on top of cold.
I have some blob of warm water inside a cold
So
system.
then it rises up. Yes, okay.
It will rise up. So if you want to test it, you can put salinity 3 and see what happens. Rerun the simulation. Oops. Okay, wait a second. I did something wrong here. So to test it, just put constant salinity equal 4. Rebuild of the model. Where are we here? Rebuild. Oops, what did I do wrong here? Parse error. Oop. Yes, thank you. Rebuild everything, and let the simulation run.
How much salinity do you have to add to remove the maximum density peak?
We could test it. I don't know. It must be somewhere around 20 or 10 maybe. Well, but with 4 it will definitely rise, but you'll still see that you're gonna have edges that are denser. So you're gonna have a denser system of the border, but a lighter blob in denser water around.
Yeah, okay.
I'll show you now when the simulation finishes.
Can I have a question?
Yeah.
ClimaOcean, I'm used to having, these compile parameters and these runtime parameters. There's no such distinction in Oceananigans.
What do you mean by compile parameters and runtime parameters? Like, for example?
Well, like I choose the grid,
Uh-huh.
I choose the whatever packages that I'm going to use. These
Uh,
are like compile time.
No.
The compile is manual. Here, I think my understanding is everything is going to be you have to rebuild, but it builds fast enough anyway.
You have to rebuild. I mean, if you want to rebuild, you have to build the model. The model is actually what holds all the state vectors. So you have to rebuild the model or specify whatever parameter you want. But the parameters are there's no time in building these types because these are just they just specify what physics you wanna give to the model. They don't hold any vector. They don't need to be initialized. The model is what holds the whole the whole state vector. Did this answer?
Yeah, I think it does, but that means, for example, if you just wanted to like increase the number of time steps, it's the same thing.
Time steps is held by the simulation. So then the simulation is a mutable type.
I see.
So you can stop it, change it now the time step size, increase the stop time, decrease the stop time, increase the number of stop iteration. So the simulation, once you have a model, the simulation you can change it how you want.
You can probably use model parameters, JL and strokes and just change
What is that? Model parameters?
model parameters, it's just a way you just wrap any of the parameters in a param wrapper and you can refill
Ah,
sort them all out.
ah, nice.
Change them all quickly.
Ah, nice.
Give them as a table as JL parameters.
But so I guess my part of the answer to my question was the number of time steps that is in the simulation as opposed to the model itself,
Yes,
which there was a choice that was made at some point that the salinity was in the model as opposed to.
because the salinity is part of the physics. Physics, numerics is all in the model. The simulation just is the driver, let's say, of the model, of the simulation. Tells you how long you have to run, what is the time step. All the callbacks, all the output writers are part of the simulation.
Oh, no, thanks. That explains.
Okay.
I think it's because the initial variability test is very small compared to what happens with the endings, but it's still there's probably due to numerical or the numerical difference.
What?
Because it's just not exactly because you have t equals 0 and t equals 7.
Yeah.
So that's why it's not.
That is weird, but. Okay, so now we can revisualize this will take a little bit, so I'm gonna show it when the visualization has completed. So, does somebody have any other question on the non-hydrostatic model?
No, I was.
Yeah.
If you can give me a little time to run some of my notebooks after.
Sure.
Because we have
What time is it?
Well, we have 35 minutes left. So if you give me
Shoot.
20
Okay.
minutes, that'd be great.
Oh my God. The ocean model is a little bit longer to run. So if you guys wanna look at it, yes, just let's do it quickly. So the global ocean simulation is in globaloceansimulation.ipymb. If you guys wanna go to that simulation. This will run a complete ocean simulation on a tripolar grid. That it's a grid that has 2 poles in land and 1 pole in Antarctica, to avoid the problems with the North Pole that Gael was talking about this morning. I don't know if we have much time to do it, but I'm probably gonna go. Yeah, I can show it quickly. You guys okay with the non-hydrostatic test case? Okay, perfect. So if you open this this notebook, again, add all the packages that you need. In this case, please add Oceananigans at main because 2 days ago we had big problems of computational efficiency on CPU that have been solved. So if you don't do it, it's going to be very slow. If you don't add main.
Just check, if you do adding, you have to restart your session.
Yeah, you have to restart your session. Yeah. Yeah. Then we add ClimaOcean. It's not necessary that you add that main. You can just add the latest version. And orthogonal spherical shell grids, that is the package that constructs the tripolar grid. Syntax error. Oh, I don't need this. Oops. What? Python kernel. Let me just do this maybe. Okay. Now, to build a global ocean domain, the process is the same as we did before with the non-hydrostatic model. So first we build a grid. The grid in this case will have a vertical coordinate. In Oceananigans, we don't have all the vertical coordinates that ROMS has, but we have two. Just a normal z coordinate that is depends on geopotential, and a z star coordinate that is a free surface following coordinate. So it will change to follow the free surface. And we have a utility in Oceananigans to build an exponential array of z values, because in the ocean you really want to have the top layer that is much finer than the bottom, because nothing really goes on in the bottom of the ocean, but a lot happens in the upper ocean. So you want to be able to capture what is happening at the top. So in this case, I mean, I'm using only 10 vertical layers, which is very little, but just to make this simulation run on your laptop. Otherwise, we'll probably want to use 60 to 100 vertical layers. Because you see that the first layer is at 73 meters, which is quite deep, and it goes all the way down to 5,000 meters, which is not really the depth of the ocean. You probably want to have 6,000 meters, but for this tutorial is enough. And you see that the last element has a size of about 1,500 meters. So you have a grid cell that is about 15,000 meters high, 1,500 meters high, which is not that ideal. But this is usually the compromise that you have to do in the ocean, that the bottom cell has to be quite thick. By the way, if you want to use a z-star following, a free surface following coordinate, you just specify z-star vertical coordinate R faces. But in this case, we're just using z coordinates, so we just take what we defined. Now, the grid, in this case, is a tripolar grid. So it's this weird grid that can be described as a matrix. So this is nice because it doesn't have all this complexity of a cube sphere, but allows you to hide the singularities of the poles in land, so specifically in Canada and in Russia, because you have two big land masses where you can put the poles. In this case, I'm specifying a resolution of about 1.5 degrees. So this is a non-eddying model, which means that you're not going to have turbulence because you don't have the resolution that is high enough to resolve turbulence, which means that the ocean will look more like honey than a real ocean. But this is what we have to do because we cannot really resolve the turbulence in the ocean. To do that, you need at least 1/6 of a degree, which means about 2,000 cells in one direction and 1,000 in the other. Arc not defined, cool. Okay. Boom. Now I just want to show you how this grid looks like. It's kind of funky. Okay. You cannot really see it. But latitude lines and longitude lines look like this in this grid if you like splat it out. So this is the North Pole that is repeated on the two sides. So basically what happens in this grid is that this part is folded across. So you have one pole, and these two are the numerical poles of the grid that are situated here and here. And then there's a pole at the bottom. Probably I can show it better here. Oops, where's the... Yeah, so the grid looks like this. You have two poles and one at the bottom. And this is the side that is folded on top of itself. Okay, now we have to add the bathymetry. So as I said before, we have this regrid bathymetry option that downloads the topo bathymetry and regrids it on top of your grid. That file is 500 megabytes, so I'm not going to make you do that. So I have downsampled the file and uploaded it to Dropbox. So now this is only 700 megabytes, and you should be able to download it pretty quickly. And to this regrid bathymetry, you can specify a file name and a directory to specify which file to take to regrid the bathymetry, and you eventually have a bottom height that I'm regridding here. So if you see, the North Pole is here, that is connected on this side, so you can represent the topology of our grid as a matrix. And the two numerical poles are in Russia here and in Canada here. All good? I guess yes. Sorry, I forgot to say. We include a bathymetry in a grid in Oceananigans by specifying an immersed boundary grid, which means that you are fitting a bathymetry to the grid, and certain cells are land, so they're not active, and other cells are fluid, so they perform the computation. So you have kind of a steppy immersed boundary inside your grid. Okay. Now, we have to specify the numerical details. This is not necessarily required because we have defaults in our ocean simulation function, but I just want to show you what you have to specify. In this case, we're given a momentum advection, a tracer advection scheme, and we are specifying a free surface, which in this case is a split explicit free surface. So the free surface can be solved in different ways in an ocean model. You can have an implicit representation, an explicit representation. The problem with the free surface is that the time scale of propagation of gravity waves is extremely fast. So if you would solve it explicitly, then you would have to time step with a time step of 10 seconds. And that's something that you really don't want to do. So you can do it either implicitly or split explicitly, which means that you substep the free surface and then you step all your other quantities. In terms of physical parameterizations, since the grid is very coarse, we have to pump in some diffusivity in this model. So here I'm specifying a Laplacian diffusivity with a viscosity of 5,000 meters squared per second and diffusivity of 1,000. We also need a model parameterization that tells us what happens when you convect. This is a hydrostatic model, so we cannot represent convection in this model because convection is a vertical acceleration and we don't have that. So we need to increase the diffusivity when the state wants to be unstable. So when you start having cold water on top of the hot water, we need to diffuse it quickly. Basically, this mimics the effect of convection. And in this case, we specify a convective diffusivity of 5 meters squared per second and a convective viscosity of 5 meters squared per second. Then we also give a background that represents basically a turbulence in the interior of the ocean that is typically associated with internal wave breaking, and internal wave breaking, especially on bathymetry. I'm going to skip the restoring term. Don't look at it. This is if you want to relax your quantities to a climatology, in this case to the ecoclimatology. This is the important function that builds the ocean simulation. So we are passing the grid and all the other numerical details to the ocean simulation, and we're building a predefined ocean simulation on this grid that will have already all the configuration to accept exchange fluxes between atmosphere and the ocean, and all the drag, for example, is going to be by default prescribed. This is a simulation. It's not a model. It's a simulation. So it has a simulation of a hydrostatic model. Again, we can initialize our ocean model with, oh my God, this is starting to download. This will take a while because I wanna initialize my model with ecoclimatology, and apparently in this folder I don't have the ecoclimatology. So this function will start downloading the ecoclimatology and interpolating it on the model that we have. I think I'm kind of out of time, but this part shows you how to add an atmosphere. In this case, I would really like to show you how to add a realistic atmosphere that comes from the GRA55 analysis. But this is about 15 gigabytes of data. So you can do this, but you have to be ready to download 15 gigs. If you want to do it on your own, that's completely fine, but maybe not here so that we don't overwhelm the internet. So instead of doing that, here I have specified how to just set a prescribed atmosphere. This atmosphere will depend only on the latitude direction, so it's idealized. So it doesn't really matter what is the size of the grid that we specify. We just have to build a grid. In this case, a latitude and longitude grid, a certain range of times. So our atmosphere will be defined in this range of times, and we just build a prescribed atmosphere. And then we set the value to the prescribed atmosphere. Oh, this is taking a while. Once all this is done, we are in a good position to just build our Earth. So this will be Earth model. Will be an ocean sea ice model. This is kind of a misnomer because we started calling it like this because we thought that this would be only an ocean sea ice model coupled. But we figured out that this was actually a very good prototype to have a complete coupled model. So this accepts an ocean, a sea ice model, and an atmosphere, and time steps everything. And in a month or so, you'll see this working with Milan's atmosphere, hopefully. So this will be a speedy weather atmosphere. We build a simulation on top of the model, and that's basically it. We add output writers to as we did for the non-hydrostatic simulation, to save down some variables, in this case U, V, T, and S. And we also add speed, because that's something that we like to save, to look at the speed at the surface. That is square root of U squared plus V squared, and the free surface. And we add another progress function, exactly like before. In this case, I'm showing the iteration, the time, the wall time, the maximum of the U velocity and the U velocity every 10 time steps. And then you just run the simulation, and that's it. And you have an Earth system model. Let me see if I have the output here that I can show you. Nope. Oh my God. Sorry. In the end, you'll get something like this if you run everything through. So you get an ocean at 1 degree. We run this only for 30 days. So in 30 days, nothing happens in the ocean. The tracers are basically immobile, but at least you'll see the velocity of the ocean kind of balancing on the density initial conditions. So density will, because of geostrophic adjustment, you'll produce a flow that wants to be aligned with the pressure gradient. So this is what's going to happen. Oops, let me play this video. And you start having a flow. It is a honey ocean, so not really much turbulence going on. But this is what it will look like. So you'll have a strong current in the equator, the southern ocean that will react to the horizontal density gradient in the southern ocean, and a free surface that will adjust to the density of your ocean. Temperature and salinity do basically nothing in this time period. They are kind of still. Well, if you do the same thing with increasing resolution to 1/4 degree, for that you need a GPU. So basically what you would do is just switch this one to GPU, increase this one to 40 maybe, because we need a little bit more vertical levels, and increase these NX and NY to 1/4 degree, so that would be 1440 and 700, roughly speaking. and increase the order of the advection scheme. Plus 2.5. And remove the eddy closure, because at high resolution we don't need the eddy closure. I know it's a little bit fast, but I just want to show you the results, because I'm going a little bit over time. So what you'll get is something like this. Same exact simulation, only doing those changes. So this is a quarter-degree ocean, so you start seeing eddies develop. You see the ocean responding to the atmosphere that's blowing on top of it. This with the JRI 55 prescribed atmosphere, as not with the idolized atmosphere. You'll see eddies developing in the sea surface. Still, temperature and salinity do not do much, but at least you see some eddies developing. I think I'm a little bit over time, so. Sorry. Sorry if I was a little bit long on the thing. And
So I wrote the little proof that I had after, and I think we do that instead of the panel discussion.
Yeah.
Like 420.
Yeah.
That's 4, whatever.
Yeah, unfortunately we had this power outage that cut stress sessions a bit short.
Yeah.
That's good. So I'll do them at 4 and it won't be very long.
Yeah. Try the global ocean simulation, huh?
Yes.
Try it out.
Thank you.